This is Dr. Palnivel Rajan. I am Associate Professor from ECE Department of Electronics and Communication Engineering from M. Kumarasamy College of Engineering, Karur. So, welcome to this session regarding measurement and instrumentation. So, now I am going to tell you the basic concepts involved in measurement and instrumentation, as well as what are all the functional blocks or functional elements present in the instrument, and what about the performance characteristics, for example static characteristics and dynamic characteristics, and what are all the possible errors present in the measurements, and how we can able to evaluate the measurement data, that may be the statistical evaluation, and the direct and indirect measurement of measurements, the classification of instruments along with the standards and the calibration. But this session we are going to concentrate on the basic terminologies. So what are all the basic terminologies we are having in this measurement and instrumentation, and what are all the basic functional blocks for the for an instrument. So that will be the first discussion, okay, after followed by the static and dynamic characteristics. Why? In the sense this may leads us to the performance characteristics of any instrument. So this static and dynamic characteristics plays a major role whenever we are talking about any kind of equipment or measurement, maybe the instrument, whatever may be. So that's why for measuring the performance of this instrument, so we are in need of such a kind of static and dynamic characteristics. Let us see one by one. What do you mean by this static characteristics? What do you mean by this dynamic characteristics? Everything we will be looking by the following slides, and whatever the possible errors possible in the measurement, possible errors in the measurement. So that we need to clarify before getting into these standards and the calibration. What are all the methods, evaluation methods available for this measurement data? Fine. So these are all the presentation agenda I am having over here. The very first thing is, what do you mean by the word called measurement? So it is nothing but comparison. Okay, comparison. What we are going to measure. Okay, and what about the standard values available for the particular parameter? Okay, so for example, if we are going to measure a heart rate or heartbeat or blood pressure, so for each and everything we are in need of a standard value, right? So for example, I'm taking the value of a heart rate. So the normal heartbeat level is 72 to 76 beats per minute. This is going to be a standard value, and we are going to measure our own heartbeat level or heart rate level. Same thing will be applicable for this blood pressure measurement also. So in blood pressure measurement the standard value is 120/80. Fine. So this 120/80 is going to be the standard value, and we are going to measure our own parameter, own blood pressure measurement. So this is going to be the best example of this word called measurement. Okay, so the measurement is something but the word called comparison. Okay, comparison means we are always having a standard parameter, a standard value here, and based on that standard value we are going to compare our own performance, our own parameters or performance, whatever may be the quantity. So it is going to be a measurable one. So that will be gives you the clear picture about the measurement. Okay, and the measurement will be actually is a science of determining the values of physical variables. So whatever the physical variables we can able to measure, for example example, air humidity, as I already told you about the heart rate value, blood pressure value. So everything will be the example of physical variables or physical quantity. So these are all the things we are going to see whenever we are talking about the measurement. Fine. And the equipment or the setup we are using for making this measurement, that is called the instrument. Okay, so you just know what is measurement and instrument, and what is the purpose of studying this measurement and instrument. That is very, very important over here. Before getting into this topic, we need to clarify how much amount of data can be measured, and what quantity of data, and what we need to compare. So everything will be taken into account. So measurement in the sense we are going to compare our own measured value with the standard values or the true value. Okay, so that is called the measurement. The setup or equipment we are using for making this kind of measurement is called the instrument. So the very basic requirements or only two for any kind of measurement. So first one is it should be very accurate. So whatever measurements we are doing, maybe in our home or in our laboratory classes or in our routine life, so whatever the measurements we are doing, it should be accurate as much as possible. We cannot able to achieve 100% accuracy. So as I already we have discussed in the previous session, so 100% accuracy is not at all possible. So is it possible to design a error-free system? That is, I am talking about the ideal system. No, it is not at all possible. So in the practical occasions, without any error, okay, without any error, we cannot design any system. Okay, we cannot design any system. But even though our intention is that to minimize the error as much as possible. So how much we can able to minimize the error, that much the system is efficient, that much the instrument is efficient. Fine. So our intention is that our as a electronics engineer or our communication engineers, our ultimate contribution towards how to minimize the error. So that is our best requirement. For almost the most requirement of any instrument is to be the accuracy. That is point number one. And point number two is whatever the apparatus or methods we are using for our own measurement, it should be provable already. It should be provable already. So that is going to be the second basic requirement of an instrument or any measurement. So these are all the very basic requirements what we are expecting for the word called the measurement, you know. So next thing is about whatever the physical quantities. So I told you, right, so there are various physical quantities are available. As I told you, temperature, pressure, mass, length, so everything will be the best examples of the physical quantity. And whatever the data we are deriving from that particular parameter or quantity, right, so that is called to be the data what we are going to measure now. And the information and the parameters associated with the physical quantity. So that are all the parameters, that are all the parameters or quantity we are going to measure by using this kind of the measurement value with the standard value. So it's a standard value. So why we need to study this measurement? That is very, very important, right? So first we have to see what is measurement and what is instrument, and what are all the basic requirements of measurement and instrument. And in addition to this, we have seen a few physical quantities. Is it possible to measure, right? Yes, with pressure, temperature, heart rate, and the blood pressure measurement, everything we have seen. So please be very clear about it. So we need to maintain the accuracy. That is our almost the most important objective of any electronics or communication engineering, to be the to maintain the accuracy level for any kind of instrument or equipment. And in addition to that, we have to improve the quality of the product, right? So we have to improve the quality as well as the efficiency, and we have to ensure the proper operation of the instrument. So these are all the terminologies linked with the accuracy. Okay, we are in need of quality. Okay, so the equipment or instrument which is producing very high accuracy level may be the quality equipment or quality product, and it may improve the efficiency of the production or efficiency of the product, and it may can give us the consistent operation, maybe the proper operation. It should not go for any kind of malfunctioning or improper operation, right? So we are interested to go for these kind of measurements with these kind of the requirements before getting into this design of any kind of instrument or equipment. Okay, very important thing is, as I already told you, we are in a position to compare our own parameters with the standard values. Fine. So standard values always be there, right? There is no doubt in this. As I told you, just to take as an example of blood pressure measurement. Okay, our human blood pressure measurement standard value is 120/80. We know already, right? So that is going to be a standard value. That is going to be the true value. Now what we are going to do here is, we are going to compare, we are going to measure our own blood pressure. For example, as an individual, I am going to measure my own blood pressure measurement. I am going to compare my measured value with the standard value, that is 120/80. That's 120/80 stands for 120 stands for systolic and 80 stands for diastolic pressure. Fine. So this value, measured value, going to be compared with the standard value, that is 120/80. So this kind of comparison is called measurement. Okay, so always the value has been predefined. Okay, it has been universally accepted value, that is 120/80. It is going to be the universally accepted value. So we are going to compare our own parameter with this measured parameter, with this standard value. There may be some deviation, right? So it will not be exactly equal to each other. For example, 120/80, right? It will not exactly equal to each other. So there may be some sort of deviation may be there. That deviation refers to error. Okay, as I shown in the slide itself. So it's a difference between the measured value and the true value. Okay, always we are having some sort of expected value or desired value. It is always keep in our mind. Okay, so for any kind of examination process or any kind of routine life, we are expecting something, but it's happening somewhat deviating from the expected level. So that kind of deviation will be the error value. What should we do? So our intention is that to minimize the error as much as possible. To minimize the error as much as possible. So the minimization of error is one and only the contribution should be made by any electronics or communication engineering or any manufacturing engineering. Okay, maybe the measured value, true value should be closely packed. It should be closely equal to each other. Okay, then only we can expect a minimum level of error. As I told you, the difference between this measured value and this true value may gives you the concept called error. Fine. So these are about the these are all the mechanisms of what we are going to discussing over now. But before getting into this error measurement, we should know the performance characteristics, right? So what are all the performance characteristics available for making this measurement on or any kind of instrument to be make it in a better way of measuring the quantity or any kind of physical parameters. So that we need to understand. Fine. So before getting into this physical parameters, performance characteristics, we are interested to know what are all the very functional blocks are available under this measurement of instrument. Okay, so this slide will gives you the functional elements of an instrument. Primary sensing element. Okay, I told you in a broad way we can classify into three types. One is a primary sensing element, and variable conversion element, and the data presentation element. So what we are supposed to going to do here is, just for example, we will take the heart rate measurement or blood pressure measurement. Just for example, I'm telling you. So we are going to measure the heart rate of any individual, or we are going to measure the blood pressure of any individual. So what we are supposed to do, we are in need of any transducers or any sensors we are in need of, and with the help of this transducers and sensors, we are going to get a physical digital value, maybe about heart rate or blood pressure level. Fine. So that sensing element is the primary element of any kind of instrument. So the primary sensing element is that maybe any kind of transducers or any kind of sensors. What is transducer? What is sensor? It's an enhanced version of transducer is going to be your sensor. Fine. So what is the job of transducer here? So it is going to convert any kind of energy or parameter or signal into the electrical signal. That is the primary job of transducer. So this transducer and sensor is going to be the primary or the first block of the instrument. After that, we are having data conditioning element, maybe contains data variable conversation element and the data presentation element for visualizing the output, what we are extracting or what we are trying to do. Okay, it may be the digital value or it may be the wave pattern. So whatever it may be, so it can be visualized by using any LCD or LED displays. It is possible, but the first foremost step is we are in need of the sensing element. It may be the transducer or it may be the sensor. Fine. So this is the inference from the slide, and the detailed explanation will be given in the upcoming slides. And we are supposed to concentrate on the performance characteristics of an instrument. So what are all the performance characteristics? Okay, so once I told you about the performance, you should understand two different types of performance analysis should be happening in the instrument side. It may be the static and it may be the dynamic. What do you mean by the word called static characteristics, and what do you mean by the word called dynamic characteristics? So very simple. If your ultimate performance measure or performance maybe your measurement value, okay, it is going to be constant and isn't going to vary with respect to time, that is called a static characteristic. Okay, whatever the parameters you taken as an example, maybe the accuracy or sensitivity, I have listed out totally 16 static characteristics in the slide. So out of that, none of that characteristic can able to change their nature or characteristic with respect to time. Okay, it is going to be kept constant throughout the process or throughout the span of the instrument. Okay, it doesn't going to vary with respect to time. That is called static characteristics, or else some negotiable changes may be there. Maybe if you are measuring the current level of 5 ampere, okay, 5 ampere, maybe your friend may get the value of 4.9 or 5.1, like that. That kind of small variation always be there, so because of the instrumental errors. So that is possible. So that is also considered as a static error. What do you mean by the dynamic error? So whatever the parameters, whatever the characteristics we are supposed to analyze, that particular characteristics is going to vary with respect to time. Okay, it is not going to be the constant value. That particular characteristic is going to vary with respect to time. That is called the dynamic characteristics. These two things, maybe the static and dynamic characteristics, going to bring you the performance characteristic of any instrument. Fine. So whatever the characteristics measure we are going to do here is only for designing an equipment or instrument. As I already told you, we are in the position to minimize the error as much as possible. Fine. So we cannot able to design an ideal system. Ideal system means system without any error. It is not at all possible. So whatever the system or whatever the equipment or whatever the instrument we are trying to design, we should aware about the standard values, and we should aware about the standards what we have to follow, and our measured value, our observed value should be as much closest to the other standard value. Then only we can able to achieve very high accuracy, and we by suppressing the error, maybe by minimizing the error. Okay, so we cannot able to design an ideal system. It is not practically possible. I am repeatedly saying. So system without any error, okay, it's not practically possible or reliable one. But based on our own analysis, we have to compare our performance, right? So for that only we are talking about the ideal system. But even though our error minimization speaks a lot, whenever we are talking about the performance characteristics, this error minimization is very, very important. So without error minimization mechanism or techniques, it is very difficult for the observer or user to do the readings, or taking the readings from the instrument, or any kind of observations. It's very, very difficult. Okay, so let us say for example, in our laboratory classes, you are taking the readings, okay, then and there. Okay, the same equipment or instrument you are using for all the mostly you are having 5 batches in the session. Okay, all the 5 batches are going to use the same level of equipment or instrument. That is no fault finding in this. But even though maybe the observation timing may be differ, maybe at 10 o'clock you are going to do the experiment, or at 10:15 your friend may be going to do the experiment, but your observation going to be the same. Okay, so for example, I'm telling you, if you are measuring the current value, if your measured value is 5 amps, in the sense that 5 ampere of current should reflect in all the 5 batches readings. Okay, if there is any deviation in this, that should be negotiable within the limit. For example, I'm talking about 5 ampere, in the sense you can get it as 4.9, 4.95 or 5.1. So within that limit, if any deviation is there, it is going to be the acceptable one. Okay, it is going to be acceptable one. But the deviation is very large, maybe very far, maybe 5.5 or 6 ampere, in the sense that is not a correct way of measuring the. Either your observation is wrong and your procedure may be the wrong. Okay, so that kind of analysis we have to do whenever we are supposed to take a reading from a particular instrument. So this will brings you the performance characteristics of any instrument. Okay, so if the performance of the particular instrument is very correct or pakka, so that kind of performance, that kind of instrument may gives you the very high accurate readings. whatever the measurement may be. Okay, so that is our intention of measuring studying this static and dynamic characteristics. Okay, so the entire analysis will be based on the static and dynamic characteristics. So in upcoming sessions also we are going to discuss maybe analog ammeters or voltmeters or permanent magnet moving coil meters, instruments, or any kind of moving ion instruments. Okay, so multimeters. So these are all the things we are going to discuss in the upcoming sessions, but our basic expectation is we want to minimize the error as much as possible by considering these characteristics, maybe the static characteristics or the dynamic characteristics. So whatever the static and dynamic characteristics we are supposed to use, we are going to consider. Everything will speak a lot whenever you are framing a technical specifications of any instrument. So just for example, you can take the technical specifications of any equipment. So whatever the equipments you are using, maybe in your routine life or in your laboratory, you can go for it. So everything, whatever the parameters we are going to discuss now, everything will be specified in a very keen manner. Okay, so everything will be accountable, right? So then only we can able to expect the high level of accuracy in the equipment or instrument what we are trying to do, or we are supposed to take the reading from the particular instrument. So that is going to be the purpose of studying this kind of characteristics, especially the performance characteristics. So this is going to be maybe divided into only two types. One is static and dynamic characteristics. As I told you already, this characteristics is going to vary with respect to time. That is called dynamic characteristic. Okay, it is going to be kept constant, or some kind of negotiable amount of variation will be there, in the sense that is called the static characteristics. Totally 16 static characteristics are available over here. Okay, so as I shown you on the slide itself, maybe the first one is accuracy. Okay, so this is going to be the very important characteristic, one of the important performance metric or characteristic of any kind of instrument. So that is going to be the accuracy level. Then sensitivity, then precision, reproducibility, repeatability, drift, static error, drift zone, threshold, stability, linearity, then span of an instrument, then bias, tolerance, true value, and hysteresis. Okay, so these are all the 16 parameters under this static characteristics. Fine, so let us see one by one. What do you mean by the word called accuracy? Okay, so accuracy in the sense, as I told you about the standard values, that is called universally accepted values. Okay, our own observed value or measured value, both should be as much as close to each other. Okay, so it should be close as much as possible, then only we can able to minimize the deviation, through which we can able to achieve the very high accuracy by minimizing the error also. So how close the measured value with the standard value, that is going to be your accuracy. Okay, so that is why it is given in the slide itself, how far how nearly this measured value is approaching the true value or standard value of the particular quantity, that is called the accuracy. Okay, so this is going to be the key factor or a very important feature of any kind of instrument. So whatever the instrument we are supposed to design, or we are supposed to are going to take the readings from the particular instrument, so always we are expecting the 100% accuracy, not exactly 100%, maybe closely to 100%, maybe 99% of accuracy and 97% of accuracy. So this is going to, without this accuracy we cannot trust the instrument or the equipment. Okay, so this equipment has to be trustworthy, right, based on the accuracy level. How far the accuracy level is going to be closely approaching the value of 100%, maybe about 99, maybe going beyond the 99% of accuracy. And this kind of accuracy can be of three types. One is the point accuracy, and accuracy of scale span, maybe with duration of the equipment. Okay, and the true value, percentage of true value. So how this instrument is going to be closely linked with the true value or standard value. This standard value is going to be the universally accepted value. Okay, whatever the physical quantity or parameters we are going to measure. Fine, so let us take for example, I am telling you about the temperature. Fine, it is going to be one of the important physical quantity. So what is the standard value of human body temperature? It's about 98.6 Fahrenheit. fine. So this 98.6 Fahrenheit is going to be universally accepted value wherever you go, not only in India. So if you are going for any abroad countries, maybe US or London or whatever maybe, this value is going to be kept constant. Okay, we are going to measure our own parameter, our own temperature value with the standard value, maybe about 98.6 Fahrenheit. So this is called the accuracy measurement. Okay, how closely we are approaching the standard value. If you are crossing the value, that will be considered as going to be the fever. Okay, and the sensitivity, and a very important character, maybe parameter also. It may be the some set of response the instrument has to give it to the user or the maybe the observer. Okay, for each and every input, okay, whatever the inputs we are giving to the particular system or the equipment, there should be some set of response we are expecting from the particular instrument. So that's why it is going to be the changes in the output of the instrument, okay, for each and every value of the quantity what we are going to measure. So that is going to be the sensitivity. So how sensitive we are, right? So for each and every small kind of variation in the input signal, which may gives you some kind of set of maybe the vast response or a rapid response we are expecting from the instrument. So that is called the sensitivity. And these are the plot related to the sensitivity. Okay, how the changes in the input output will be divided by the changes in the input. Okay, so if any changes in the input, which may surely reflect in the output. Okay, so that difference, that ratio is going to be considered as a sensitivity. Okay, so this is going to be more important factor whenever we are talking about any kind of instrument or equipment. Precision, so it is going to be the measure of reproducibility. Okay, so that is given as a fixed value. So how much we can able to reproduce, okay, how long you can able to reproduce the fixed value or the variable, what are the physical parameter or quantity what we are trying to measure here is that is called the word called precision. Okay, so precision is nothing but the successive measurements which may differ from each other. Okay, which may differ from each other. So that is going to be considered as the precision. So this is also one of the dynamic static characteristic of any instrument. Then next one is repeatability. So it is going to be the degree of closeness. Okay, as I told you, right, closeness in the sense what the measured value should be close, maybe close enough to the standard value or the true value. That is going to be your repeatability. So how far the closeness of the output reading when the same input is applied. Okay, maybe the same input is applied whenever we are applying and wherever we are applying, but for the same input we should expect the same output what we are getting maybe within the span of time or short period of time. So that is going to be the repeatability. Okay, you should not give the different values as the output. For example, at 10 o'clock I am taking reading, it will be showing as a 5 volts, and as maybe 10:30 some of my friend is coming and taking the reading. Okay, in that time it will be giving its reading as 10 volt, in the sense there is no meaning in it. So that going to be the word called repeatability. Okay, so reproducibility I told you already. So how far the system is close to the standard value or the true value. Okay, that is called the repeatability. And the drift, so the drift is nothing but so the output of the instrument, okay, the departure, so that may be some kind of deviation. So deviation will be in the output of the instrument over the period of time. Okay, so drift is going to be considered as a maybe it may unrelated to the operating conditions or the load what we are using now. So these are all the parameters or factors what we have to consider for making this drift to be under control. Okay, so these are all the parameters: wear and tear, and mechanical vibrations, stresses, temperature variations, and the stray electric and magnetic field. The stray electric and magnetic field is a very big challenge for the manufacturers. So what we have to do, okay, especially among the 6 I have listed out wear and tear, mechanical vibrations, stress, temperature variations, stray electric and magnetic field, and thermal EMF. Out of the 6, this 5th one, stray electric and magnetic field, requires a shielding effect. Okay, this shielding effect may reduce the drift. Okay, so the shielding is gives us the enormous, I mean the surprising result, surprising output, okay, whenever we are measuring it in the equipment or any kind of instrument. Okay, so this is about the drift and the static error. So error we have already discussed. It may be the comparison between the observed value or our measured value with the standard value or true value. This difference is going to be considered as a error. Static error means your unknown quantity is in your hand, but you have already know the universally accepted value. For example, I told you about the blood pressure measurement, heart rate measurement. Everything will be comes to a picture. As an example, we can take it as the comparison. Okay, so whatever the comparisons we have made, so everything we should have the everything should be based on the standard values. Okay, whatever the standard values we are having, okay, that standard value is going to be the reference value. So based on the reference value or standard value, we are going to measure our own parameter. That's all. So that is called the comparison. This comparison always gives you some set of error. Okay, that error will be minimized. Okay, should be minimized as much as possible. So this kind of error minimization is always possible. Okay, if and only this closeness should be as much as possible. What closeness? That observed value should be close with the standard value or the true value. So this kind of closeness will give us the better result. Okay, that difference is called, the deviation is called the static error. Okay, and dead zone. So this is going to the largest changes in the input quantity for there is no input, no output. Okay, so whatever the inputs we are giving to the particular system, this is say as an example of only one system. Okay, if you are going to measure, any kind of parameters from the particular system or equipment, for that we are going to give some set of input. Okay, always a characteristic of a system will be given by the transfer function. Okay, transfer function means what? The transfer function is nothing but the ratio of output to the input. That implies that whatever the input we are feeding to the system, it should be reflecting in the output end. Fine. Now what is the dead zone? In the sense, whatever the changes we are making in the input side or input portal, it will not be getting reflecting in the output side. It will not be reflecting in the output side. So that is going to be the dead zone. Okay, so whatever the advice we are giving, okay, if you are taken into account, in the sense, that is not a problem. Somebody is advising us continuously, but we are not worrying about, or we are not taking care of such a kind of advice, but we are doing our own job, in the sense, that is called dead zone. Okay, so we are taking our own decisions. We are not taking care of the inputs what we are receiving, right? So that is called the dead zone. Okay, and the threshold. So whatever the parameters or whatever the analysis you are going to do in the circuit wise or any kind of instrument wise or any kind of signal analysis, everything will be having a word called threshold. Okay, so just for example, your academic record will be the best example of threshold. Okay, what is that? If you are getting 50 marks or more than 50 marks, then you will be awarded as a pass mark or a pass percentage, or you no need to reappear for the particular subject or the thing. So that is called the threshold. Okay, you have to fix your own value. That is going to be your minimal allowable limit. Okay, minimal allowable limit. So below that will be considered as a poor performance. So that is not going to be the threshold value. Your threshold should be above that particular given value. Okay, just for example, 50 marks. So 50 is going to be your threshold value. Once you have scored more than 50 or exactly equal to 50, that will be considered as a pass. Okay, if you are scoring below 50, maybe even 49 will be considered as a failed mark. That 50 mark will be acting as a threshold over here. Okay, likewise, whatever the parameters or quantity we are going to measure, okay, as I told you in the slide itself, smallest measurable input below which there is no output change can be identified. Once your mark will be getting down, that may be below 50 marks, in the sense it may be 49 or 20 or 15 or only 5 or 0, it will be considered as failure. Okay, failure mark. You have to reappear for the examination. But if you are crossing that 50 in the sense, then you will be considered as a pass percentage, pass mark. So that 50 is going to be considered as a threshold, maybe the threshold value for the particular student or particular academic record. And stability. So whatever the analysis we have to do, okay, about the any kind of instrument or equipment, stability we need to ensure. Okay, so stability in the sense it has to retain its own performance throughout the span of instrument, that means for each and every equipment or instrument, there should be some duration, maybe the lifespan will be there. Okay, as for human beings it's about 60 years, right? So like that, all the equipment or instrument is having some lifespan. Throughout the lifespan, that outcome should not be gets reduced. Okay, their accuracy should not get reduced. It has to give us the consistent or consistent performance of measurement of any kind of parameters or quantity what we are supposed to measure. So stability in the sense we have to give a consistent performance, consistent and tracking performance throughout the span of instrument or equipment. So that is called the stability. So stability threshold almost mostly maybe interlinked. Why? In the sense the threshold value should not get changed. Okay, so whatever the measurements we are trying to do, okay, you should not have the right to change the threshold with respect to time. Okay, once you have fixed the threshold value, it is going to be kept constant throughout the process. You should not touch the threshold value until you have to change your designing considerations. Okay, that is point number one. And whenever you are considering the stability, your standard values, okay, whatever the values or whatever the observations you are getting from the equipment or instrument, it has to be matched with each other. Okay, so when today you are taking some set of readings you are getting, and tomorrow you may get some set of readings totally both the readings are not at all matching with each other, in the sense there is no use of getting that such a kind of observations. So whatever the observations we are having, okay, so in order to ensure the accuracy level, what should we do? You should not depend upon a single reading. Okay, you have to go for multiple number of readings. Then only you can able to judge whether our observation may be correct or not, right? You can go for any performance plot or performance curve. So based on that, you can able to understand whether our observed readings is correct or not. So that kind of stability we need to have. Okay, so if the stability is lacking in the sense, you cannot expect the instrument or equipment will give us the 100 maybe the same set of values or same set of outputs in all the times. It may giving you some different level of outputs maybe at different time slots. So that will not be good for the equipment, okay, or instrument. So that is going to be the one of the important parameter about the stability. Okay, and linearity. So whatever the concepts or parameters or characteristics we have discussed so far, maybe some slightly changing with this linearity concept. Why? In the sense, whatever the performance metric we are having, okay, it should be linear with the performance. Okay, so whatever the parameters you are considering, whatever the factors you are measuring, okay, everything should be aligned with the performance of the particular instrument, right? Am I right? Yes. So that is called linearity. Okay, whether you are improving your accuracy level, whether you are improving your sensitivity level, whether you are maintaining your linearity level, maybe your stability, and whatever the things you are doing, okay, everything will be aligned with your system performance or your instrument performance. If it is not so, then your system may not be linear. Okay, so that's why I'm talking about the linearity here. So the ability of an instrument to reproduce its inputs linearly. Okay, there should not be kind of a deviation. It will measure of maximum deviation of the calibration points. okay, from the ideal measurements. There should be some deviation will be there, but it should not be deviated as much as possible. Okay, it should be within the limit, as I told you, right? It may 5 amperes in the sense, you can get it as 4.9 or 5.0. That will be considered as a acceptable level. But the instead of 5 ampere, if you are getting 6 or 9 or 2, that will not be good, that will not be acceptable also. So that is why we are talking about the linearity here. And the range I told you, right? So for each and every equipment or instrument, there should be some span of time or range of time. What is that span? So within that particular allotted time or within the particular period of time, the instrument may give us a better performance. Okay, so for example, let us take automobiles. So whatever the automobiles we are having, maybe a two-wheeler or four-wheeler, it's about 15 years of time, like am I right? So this is 15 years. Within the 15 years, we can expect a consistent performance or a very good performance on the particular instrument or particular automobile. Once the 15 years gets over, maybe you may have some sort of troubles, or maybe some sort of errors may happening within that instrument or system or device. So the range has to be specified. Okay, maybe between 5 years to 10 years or 10 years to 15 years, there should be some range will be there. Okay, the range in the sense minimum value to the maximum value. Okay, so whatever the minimum value we are having to the maximum value, that will be gives you the range. The range in the sense within that particular limit, okay, particular limit, that we can expect 100% performance, or 100%, not 100%, closely 100% to the we can expect from the particular instrument. Once this range has been crossed, okay, then we cannot expect that much of performance or that much of accuracy from the particular instrument. So that is the only agenda about the span of instrument. Then bias. So this is going to be the constant error. So the constant error which exists over the full range of measurement of an instrument. Full range of measurement of an instrument in the sense that is called bias. Okay, so this bias will be eliminated by a term called calibration. Okay, so let us take this zero error as an example. I have put it over here, zero error as an example. Just for example, I am telling you how we can able to analyze whether this equipment is requires any calibration mechanism or not. Maybe you can take it as a meter or voltmeter or whatever may be. With the help of what you can judge whether this equipment or instrument requires any kind of any kind of calibration. You have to go with this pointer. Okay, so whatever the observations you are taking from the laboratory, everything will be pointer oriented. So some pointer will be kept inside the meter or voltmeter. So without any input, there is no input to the particular circuit or the equipment, you can go for the taking the reading as it is, as usual. If the particular deflection of the by the pointer is not up to the mark, for example, I'm telling you, if there is no input, okay, the pointer should be at the 0th position. Okay, but there should be some deflection will be there. Even we don't have any input to the particular circuit or particular system. So this will be considered that particular equipment requires some sort of calibration. Calibration in the sense what? With the help of standard or reference value or reference standard values, we can calibrate, or we can do some sort of adjustments in the equipment. Okay, so that this equipment also will give us a better result, just by comparing with each other. Okay, so we are having a standard or reference equipment. Okay, that reference equipment will be help us to calibrate the measurement need to be tested. Okay, so how we can able to whether this kind of calibration is required for particular instrument, we have to observe the pointer with in keen manner. Okay, if there is no input, that pointer should be at the 0th position. No, there may be some light deviation will be there, or the deviation may be the huge in the sense that will brings you calibration process. So the calibration, in the sense we are having some standard or a reference equipment or instrument. So based on that we can go for analyzing or testing a equipment. Maybe the adjustments, that exact word called adjustment. We have to adjust the equipment so as the instrument will be producing the Pakka result. Okay, that is called the bias. And the tolerance limit, this is going to be the tolerable limit. What is this? Maybe tolerable limit. So with that limit, that output will be acceptable. Once the limit has been crossed, it will not be acceptable. That is called the tolerance. Okay, so the maximum allowable error, the exact word is called the maximum allowable error. So that maximum allowable error, in the sense that level of errors can be acceptable. Okay, once that level has been crossed, in the sense what will happen, we have to discard the output. Okay, we have to discard the output. So that is called the tolerance level. Okay, true value, as I told you already, true value is something, but it's going to be the standard value. It is going to be the universally accepted value. Okay, so universally accepted value, in the sense they have gone for many research or many kind of testing. Okay, after such a kind of study or a research or any kind of observations, in number of observations, they came to a standard value or a true value. Okay, so that true value or standard value is going to be universally accepted value. I told you for temperature, body temperature, and I told you as an example called the blood pressure measurement. So the blood pressure we are getting is 120/80. Okay, and what about the normal heartbeat level or heart rate level? 72 to 76 beats per minute. So these are all the predefined standard values available already. Okay, so based on that you can able to do the comparisons, you can do the measurements. So that is called the true value. Okay, so the last one is hysteresis. It is going to be one of the negative impact. Okay, it is going to create a negative impact whenever we are taking some set of readings. So that calibration has to be conducted properly. If this calibration has to be conducted properly, in the sense we can expect different output effects whenever we are loading or unloading. So this is going to be the very bad impression about the particular equipment. It should not give that much of different output values whenever we are loading or uploading or downloading, whatever may be. So whenever we are loading, that values to be consistent. Okay, for example 13579, in the sense once you have gone for unloading, then the 97531, likewise the reading will be come down. So if there is no flow or there is no uniformity in the particular reading whenever we are loading or unloading the equipment or instrument, that is going to be the bad constraint. Okay, it is going to be, surely it may create some sort of a negative impact over the instrument or equipment. Okay, it has to be calibrated properly. Calibration, I told you already. So whenever we are having, we are supposed to calibrate the equipment. And one more discussion we need to give: how long or how frequently you need to calibrate the equipment. It's up to the case. Okay, so how frequently we are using the equipment. Okay, maybe we are continuously using or frequently using the equipment, or we are going for some set of periodical usage, maybe 3 months once or 6 months once. In the sense you can go for that level of calibration. If you are frequently utilizing the equipment, you can go for calibration periodically or frequently. If it is not so, then it will be considered to be as a not suitable equipment. Maybe it may, since it may expect that the instrument may give you the negative results or the wrong results. Okay, your observation may be wrong. Which indirectly implies that it may have the impact over the accuracy. Okay, so that kind of calibration we need to do for avoiding hysteresis loss also. Fine. And we are getting into this dynamic characteristics. Okay, so far we have discussed about 16 characteristics about the static characteristics about the performance metric. Okay, so whatever the characteristics we have discussed so far, maybe you can take a stability or span of instrument or your accuracy level or sensitivity or dead zone, whatever may be, it is going to be kept constant. Okay, it implies that it doesn't going to vary with respect to time. it is going to be kept constant. Maybe some set of deviations may be there, maybe the allowable deviations will be there with respect to time I'm talking about. Okay, it is going to be considered as static characteristics. But now we are getting into this as dynamic characteristics. So whatever the set of criteria we are going to follow here, okay, so whatever the various dynamic characteristics we are listed over here, everything will be a change with respect to time. Everything will be changed with respect to time. As I told you, the particular characteristic is going to vary with respect to time. That will be considered as a dynamic characteristics. Okay, not the static characteristics. As I told you, there are four characteristics are available over here. One is speed of response, okay, and measuring the lag, okay, how the instrument is lagging, and fidelity, and the last one is dynamic error. Okay, so what is the speed of response, lagging, fidelity, and this dynamic error? Almost speed of response, dynamic error we have already discussed. What is that? So speed of response, in the sense it can be linked with sensitivity. So how rapidly system will be responding to the observer, or how we are bringing some changes in the input side. We are bringing some changes in the input side, and how far or how fast or how rapidly the instrument is responding to the particular changes in the input side. That is called the speed of response. Okay, and measuring the lagging in the sense what it may be called delaying. Okay, delay in the response of the particular equipment or instrument, whenever, even though we are feeding some set of changes in the input line. Okay, so we are giving some set of changes in the inputs. Okay, but even though we are having some set of delay in the output line. Okay, so that kind of delay will be considered as lagging. Okay, we have to measure the delay. The delay should be minimized as much as possible in order to ensure the very good performance of an instrument. Okay, speed of response, the speed of response, it should be up to the mark. It should be as high as possible. Speed of response in the sense, whenever or wherever we are having such a kind of changes in the input signal or input quantity, that should be reflected in the output immediately. Okay, that kind of reflection should be there. So that rapid fluctuations or rapid reflections will give us the better response time. That is called the speed of response. Fine. And detection time, everything will be related to delay. And the fidelity is a very important, very new parameter. Okay, so always we are in the interest of measuring in a parameter. Okay, whenever we are measuring such a kind of parameters, the changes, okay, in the measurement quantity without any dynamic errors. Okay, even though we are measuring some sort of measurement in the sense what parameter we are measuring, maybe temperature or any kind of physical quantity, pressure, or maybe the body air humidity, whatever may be, that maybe some changes will be there. Okay, for example, air humidity. So morning, if you are measuring the air humidity level, in the sense it may be somewhat okay. In the afternoon session, if you are measuring the same air humidity level, it may be dry, right? Okay, what happened to at the night time, maybe as much as high as possible. So there may be some slight deviations will be there. Okay, with respect to time, it will be changing, right? That is called fidelity. That's the best example of called fidelity. Okay, and the second one is dynamic error. Last one is dynamic error. So dynamic error in the sense, error is always error. Maybe a difference between the true value and the standard value. Okay, this will be going to be the dynamic error. And I told you, right, this quantity is going to vary just with respect to time. That is the only difference between the static error and the dynamic error. Static error in the sense that particular error, it doesn't going to vary with respect to time. Okay, dynamic error in the sense the error is going to vary with respect to time. So that is called the dynamic error. So whether you are taking this time as a constraint, okay, time as a constraint, if the particular characteristic is going to change with respect to time, in the sense that is called dynamic. It doesn't vary with respect to time, in the sense that is called static. It may be a character, it may be a error, both are same. Okay, so we are having this kind of dynamic error. Okay, so far we have discussed about the what is measurement and what is instrument, and what are all the basic requirements of any measurement, and what we are expecting from the measurement and why we need to study this measurement and instrumentation in order to improve the accuracy, in order to improve the efficiency, okay, in order to improve the quality. That is very important, and the proper functioning of an instrument, okay, that is also very important. So this is the purpose of studying this measurement and instrumentation. And we have seen about the error, okay. So this error is going to be the difference between the standard value and the measured value or your observed value, okay. So that is going to be with the concept of error. And by minimizing the error, we have to boost up the performance characteristics, okay. And before getting into the performance characteristics, we have seen the functional blocks in any instrument, okay. Maybe primary sensing element, okay, variable conversion element, and variable presentation element. So these are all the various blocks present in the instrument, okay. So the various blocks in the sense, I have sensing element in the sense maybe the transducer or the sensors we are using for measuring any physical quantity or parameter, fine. And additionally we have getting into this performance characteristics, okay. We have discussed about the 16 dynamic static characteristics and 4 dynamic characteristics so far, okay. So 16 dynamic characteristics will brings you the effect called it doesn't going with respect to time, okay. It is going to be kept constant throughout the process. That is the best that is a inference from that static characteristics. And in dynamic characteristics, whatever the parameters we have discussed so far, maybe speed of response or lagging or fidelity or dynamic error, these 4 kind of dynamic characteristics will have a character or will have the characteristic that it may vary with respect to time. It may vary with respect to time. For example, air humidity. So air humidity, body temperature also may be getting varies. For example, if you are measuring our own temperature in the noon time, maybe some slightly higher than the we can able to get this higher value, okay, not exceeding the 98.6 Fahrenheit. That is not that is not the case, but there should be some deviations will be there, okay. Maybe in the morning time, if you are measuring our own temperature, maybe about 95 or 96. In the noon time, if you are getting it, there may be 97. In the night time, if you are measuring the same parameter, same temperature level, maybe 95 again. So these kind of slight variations will be there, okay. So that may be the best example of this dynamic characteristics. This will be this kind of error is called dynamic error, okay. So this error not as a constant level, not at the constant level, it is going to vary with respect to time, okay. That is called to be the dynamic error. So this is what we have discussed in this session. So maybe the next slide will be about the errors, okay. So whatever the errors are possible in the measurements, okay, we have seen simply 2 errors. One is static error and the dynamic error, okay. So the static error and dynamic error is going to be almost same, right? So what are all the static characteristics? What is static characteristic? It is going to be the difference between the measured value with the standard value, okay, or true value. What about the dynamic error? It is also going to be the difference between the measured value with the standard value, but it is going to vary with respect to time. Which one? Dynamic error. So this is the broad classification of errors what we have discussed so far, okay. And now we are getting into this errors, whatever the other possible errors possible in this measurement, maybe the gross errors, blunders, and the measurement errors. So this measurement errors, you know, I will come to this gross errors and the blunders in the maybe in the meantime. But in the measurement error, you know, why I am giving this much of importance to measurement error in the sense, it is an unavoidable error, okay. Whatever the instrumental error or whatever the measurement error we are having, it is an unavoidable error. We cannot able to minimize, or we cannot able to avoid such a kind of instrumental errors. Why? In the sense, from the beginning itself, once the instrument is going to be manufactured from an industry, okay, so once the industry has delivered a product, inbuilt error will be there in all the equipments. You can take it as an example of up to you. Okay, whatever the equipments or whatever the instruments you are manufacturing, okay, so whatever the products you are getting from any industry, okay, it is always having an inbuilt error. Okay, that inbuilt error is called instrumental error or measurement error. So this kind of instrumental error or measurement error will be unavoidable one, maybe the unavoidable one, but we cannot able to avoid such a kind of instrumental error. That's why I told you we cannot create or we cannot design any equipment or instrument without any error. Always the error will be there, inbuilt error will be there. That error is called instrumental errors or measurement errors. Okay, so this is going to be happening in the manufacturing side, not at the operating end. If any kind of error is going to happen in a manually or by mistake or maybe due to this carelessness, whatever maybe, it can be avoided or we can able to minimize such a kind of errors. But this kind of measurement errors or instrumental errors is always be there with the equipment what we are supposed to have. Okay, maybe up to whatever the kits or whatever the maybe CRO or ammeters or voltmeters, you can take it any as an example, but always some set of error will be there. Okay, whenever we are talking about any kind of instrument or equipments. So thanks for the opportunity given to me. So far we have discussed about the basic terminologies and functional blocks and static and dynamic characteristics of any instrument, along with the concept of error in a measurement system. So maybe I will meet you in the next session for the upcoming topics. Thank you so much.